Here we are going to look at phase diagrams for linear difference equations. Recall the homogeneous first-order linear difference equation given by the operator form a0e plus a1 all multiplied by yt equals 0. The solution for this particular difference equation we found to be yt is a function of t, where the function t is equal to c0, which is our starting value or initial value, times b to the power t, where b is minus a1 over a0. In this case, a1 is here, and this is a0 is the coefficient on the yt plus 1. What is important for phase diagrams is the line yt plus 1 equals yt, which is simply a 45-degree line in yt plus 1 space, as we'll see in the next diagrams. Each successive next value, which is the vertical axis value, is translated into a current value, horizontal axis value, via that 45-degree line. The sequence is as follows. We start by picking a point on the point y0 on the horizontal axis, which generates y1 on the vertical axis via the relationship between yt plus 1 and yt. The y1 on the vertical axis becomes y1 on the horizontal via the line yt plus 1 equals yt, the 45-degree line, in other words. Then the third step is we take the y1 on the horizontal axis and generate y2 on the vertical axis via the original relationship between yt plus 1 and yt. And then we go to step 4, which takes the yt on the vertical axis and translates it to a yt on the horizontal axis via the 45-degree line, and we keep doing this. That's what the etc. means. The time path of yt consists of the succession of points along either axis, the horizontal beginning with y0 and the vertical beginning with y1. So let's illustrate this for the case of yt plus 1 equals 1/2 yt. Okay, this comes from this formula here, yt equals y0 bt, and where b is now minus 1/2 over 1, which is equal to 1/2. So we start here with a y0, and we bring it up to the translation line, if you like, our original function, yt plus 1 equals 1/2 yt. Bring that over to the line to y1 on the vertical axis. Then from this point on the 45-degree line, which is this one here, we drop down to y1, and we put y1 back into this equation to find out what y2 is going to be. Well, we get y2 over here on the vertical axis. Then we translate that back into y2 on the horizontal axis, which then translates back via this equation to a y3 on the vertical axis, and so on. If successive values of yt approach the point at which the difference equation, here the difference equation being yt plus 1 equals 1/2 yt, crosses the 45-degree line, the line along which delta yt does not change, it's equal to 0, then yt is approaching an equilibrium value. In the above diagram, the equilibrium value is clearly yt equals 0. Now the reader should consider trying yt plus 1 equals 3 yt to see if they understand why this one, yt plus 1 equals 3 yt, why that one does not go to 0. So let's pick any line yt plus 1 equals byt. As long as it lies below the 45-degree line, yt decreases over time. If it lies above the 45-degree line, yt will increase over time. We could employ arrowheads on the movement as we did above, but this could be misleading for lines with negative slopes. So as a result, we tend not to do that, and we tend to work with, for example, here we have a cobweb kind of situation. So here again, we draw yt plus 1 equals yt, which is your 45-degree line. And now we've got a yt plus 1, which is equal to minus 1/3 yt. So we have a line here which represents the relationship between yt on the vertical axis, yt plus 1 on the vertical axis, and yt on the horizontal axis. In this case, starting with a y0 here, we drop down to the relationship itself, over to y1 on the vertical axis, which then translates via the 45-degree line into y1 on the horizontal axis, which then we plug back into this equation, and we end up with y2 on the vertical axis, which translates back to a y2 on the horizontal axis, which we then plug into this relationship again. That gives us y3 on the vertical, which translates via the 45-degree line to y3 on the horizontal, and so forth. So now let's consider what happens if we have a negative line. So here we have yt plus 1 equals minus 2yt, and we start here at y0, drop down to the line, and then across. That gives us y1 on the vertical. Then we use the 45-degree line to find y1 on the horizontal. Then we use the function here to get y2 on the vertical, the horizontal line, the 45-degree line to find y2 on the horizontal axis, then y2 on the horizontal axis, then using the relationship here, yt plus 1 minus 2yt, that gives us our y3, which translates to a y3 on the horizontal axis. And so on. Here we see that y is increasing over time compared to this one here where it's decreasing over time. Now consider a non-homogeneous difference equation. Let's consider two of them, yt plus 1 equals 1/2 yt, with the 3 indicating the non-homogeneity, and the second one is yt plus 1 equals minus 1/3 yt plus 12. Again, 12 here characterizes the non-homogeneity. So if we look at these two equations, then we get yt plus 1 minus 1/2 yt plus 3. You'll notice that it intersects here at 3. We get this dark heavyset line representing our function, 45-degree line again. We start with y0, we plug that in, we get this value over here on the vertical axis. Then we plug that back into the equation, and that gives us a number here on the horizontal axis. Plug that across to the 45-degree line, and we get the vertical axis value and so forth. And what we see here is that over time, things approach to this intersection between the 45-degree line and the function itself. Now, for a downward sloping function, yt plus 1 equals minus 1/3 yt plus 12, we start with y0 here, move it up to this function, determine what the y1 is going to be, which we then plug back in. That determines a y2, and we see here that we converge on this point here in a sort of a cobweb kind of fashion. Unfortunately, there is no well-developed approach for analyzing pairs of difference equations to parallel that for differential equations. And the absence of a geometrical approach for pairs of first-order linear difference equations implies absence of possibly representing a second-order linear difference equation via its conversion to a pair of first-order linear equations. Now, there are some places where, and in some occasions where you can do that, but for the most part, we're going to leave it at that. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.